Hello and welcome to Two Sigma Presents Deep Learning for Sequences in Quantitative Finance. My name is Rachel Malvin and I work on the engineering education team at Two Sigma. We work to empower continuous learning that fuels productivity, builds connection, and supports intellectual development through technical documentation, training, and engagement programs. I'd like to invite you all to head to slido.com and enter the event code 2SigmaPresents. We have set up a live poll regarding your experience and familiarity with deep learning. We will also be using the Slido portal for Q&A at the end of the session, so please submit your questions there at any time during the lecture. I have the great pleasure to help bring in professors and grad students to lecture on their latest research and work with employees to develop conference talks. One of my favorite responsibilities is running the Hacker Lab, Two Sigma's internal hackerspace. To learn more about our culture of learning, check out the articles on our blog Insights regarding culture at Two Sigma. At Two Sigma, we are happy to have close ties to academia. If you're a student, be sure to check out our PhD fellowships. I'm proud to introduce one of our on-staff professors. A graduate of Princeton and Stanford, David Kriegman is a professor of computer science and engineering at the University of California, San Diego. Professor Kriegman's core research is in computer vision and machine learning, and he has applied this work to diverse areas of inquiry, including face recognition, robotics, and medical imaging. His recent work on computer vision for coral ecology, CoralNet, is being adopted by the U.S. National Oceanic and Atmospheric Administration for automatic analysis of coral reef images. After the talk, stick around to ask questions to Professor Kriegman and to members of our recruiting team. And with no further ado, here is Professor Kriegman.
Thank you, Rachel, for the kind introduction and welcome everybody. First I'll repeat, if you get a chance, go over to slido.com and enter the event Two Sigma Presents. You'll have an opportunity there to ask questions and also to answer the short poll. All right, let's see. So I want to go over to the poll for a second that you've hopefully had a chance to get to. And what I see is that people have a wide diversity of backgrounds in, I don't see it yet. But I'm judging that people have a wide diversity of backgrounds that are here in deep learning. Some of you are highly experienced. Some of you have taken a class. Some of you have heard the term, but don't really know what it is. And so I hope that this lecture or talk will bring to you some ideas at every level about how deep learning can be applied in quantitative finance. So, and since Two Sigma is a highly regulated industry, just read this very quickly. Thank you. Okay, about Two Sigma. Two Sigma is a financial sciences company. It was founded 20 years ago. By financial sciences, we mean that it's a company that applies the scientific methods to finance. That is, it brings data, inquiry, experimentation, hypothesis, drawing conclusions, and applying those conclusions. We operate in a number of different investments. The original business founded 20 years ago was a quantitative hedge fund, and that has expanded out into other businesses that are closely, or not even closely, but related in the financial sector. So securities is a broker-dealer business, doing things like wholesale market making. We also have parts of the business that are concerned with private investment in venture capital, which everybody probably knows about, private equity, or real estate. And then other areas are insurance and investor solutions. So investor solutions, for example, takes some of the tools that we build internally and turns them over to institutional and professional investors through a platform called Venn, and allows them to have access to some of the same methods that we use for analyzing portfolios and investments. Two Sigma itself is, of course, more than just the businesses that we do. It's really about the people. And there are 1,600 people that work at Two Sigma, spread out mostly in headquarters, which is in New York City, but also in Houston and London, Hong Kong, Shanghai, and Tokyo. The people working at Two Sigma, 600 of us have advanced degrees, about 200 are PhDs, or even more than 200 have PhDs. Interestingly, you'd expect the finance company to be comprised largely of people with backgrounds in finance, but in fact, 60% of us don't have degrees in finance. My background's in computer vision, and I'm only learning about finance really on the job rather than coming here beforehand. And most of us work in research and development. A lot of us are engineers. A lot of us are coming from basic sciences and mathematics. They're working in the R&D side of the company. All right, so that's who we are. Now, about the main topic here at hand and why you're here. So what I want to talk about is deep learning for sequences. So let's just remember what a sequence is. A sequence is an ordered list of elements. So in this case, a sequence of length n with n different elements in it. The elements will depend upon the particular application. So if we're talking about sequences that are text, we're talking about sequences of words are the elements, or characters if it's written text. If we're talking about speech, the sequence is an audio signal, a function of time, perhaps sampled 3,000 samples per second. Music might be higher fidelity. It's a sampling perhaps up at 10, even 20,000, 40,000 samples per second. Video is a sequence of images. So one image following the other during the duration of that video of interest. But there's lots of other things that are sequences. So when you go onto your favorite e-commerce site, and you start searching around there for products, there's a sequence of product detail pages that you visit on that e-commerce site. So that's a sequence that might be of interest for processing. And finally, for our world in finance, it might be, say, stock prices. Now, sequence processing tasks are one that take sequences as input and produce sequences as output. Those sequences might be the same length, or they might be different lengths. And I'll show you some examples of this. And deep learning has had a profound impact on all of these examples, really accelerating in the last decade the accuracy with which tasks can be performed. So let's take a really simple one. Well, not really simple, but simple in terms of its output. So it was referred to as sentiment classification. Given, say, a text sequence, is the person really positive in this sequence, or are they negative? How are they feeling? Just binary, up, thumbs down based on it. So an expression might be, Jetty loved it. Their banh mi is sick. Now, is that a positive review or a negative review of a restaurant? My mother might say it's sick, nah, not so good, but anybody probably in this podcast says, no, that's a really good review. That's a restaurant to go to. All right, video activity recognition. That might be given a home video, classified as a birthday party, sports, swimming, and so on. Video is input. Single output, it's not even, it's a degenerate sequence, if you will, with just a classification score. But there are other sides of this which might go the other way. A single input producing a sequence. And so a common thing on websites is having a caption associated with an image, especially for the visually impaired who can't see it. And so given an image, you might want to auto-generate a caption for that image. Input's an image, length 1, sequence output is as long as that caption has to be. Recommendations, they generally are producing a single output, but given a long sequence of observations, which web pages you visited. Machine translation now gets interesting. You take in one language, English, and you want to translate that to French. You have two expressions in two languages. The number of words are going to be different lengths. Speech recognition takes in audio, a signal that is perhaps sampled at a few thousand samples per second, and then produces an output, which is a sequence of words, vastly different sizes of the sequences. And in our world, we're often interested in prediction. That is, how do we predict, let's say, the value of a stock, what it's going to be tomorrow? It's going to go up or is it going to go down? And that would take a sequence in the past history and produce one output for tomorrow, but over all time, it goes from a sequence of one length to a sequence of another length. All right, now let's talk about that. We mentioned the stock market. How do you make money in the stock market? Well, old adage, right? Buy low and sell high. Buy it a month ago at here, I don't know, $31.24, and sell it at like $3.80 and make 67 cents. All right, that's the old adage. And now we say buy the dip, right? And if you buy the dip and you do it really well, maybe you'll make even more money than sort of the buy high, low, and sell high predict both size of this well and, in this case, make $2.74. And you know what? Look at that plot there. There's a lot of wiggles in there. And if you add up all those wiggles and you bought every little dip at every scale, well, maybe there's more than even 274 to make on this sequence. All right, what are other ways you hear from people about how to make money in the stock market? Well, one thing they say is don't put all your eggs in one basket. And maybe that's a way not to make money, but rather how not to lose money. But that's really about diversifying your portfolio. So that's another thing you want to think about in finance. All right, another thing, don't time the market. Now that's an interesting one. You hear that expression, but of course that's runs counter to buy low and sell high and buy the dip. So we have a little contradiction in common wisdom in this one. And then finally, don't allow emotions to cloud your decision making. And in a quantitative finance, we take that very, very literally. We build algorithms, emotionless algorithms that will make the decisions. And indeed, they're making decisions like trying to predict how to buy the dip or buy low and sell high. And we'll be careful about not putting all our eggs in one basket. And that's how we'll hopefully do well in our business. All right, so in a quantitative finance, this is a typical quantitative investment pipeline, what you're seeing here. And you can find this if you grab a textbook, you'll see or a book like this one, you'll find something very similar to this almost everywhere, the pipeline of investment strategy. On the right-hand side, that's where the action's happening. That's the markets. That's where we're going to buy or sell instruments. It could be futures, it could be commodities, it could be equities, it could be options. There's a market on the other side. In the end, we're buying and selling in those markets. Now, how to make a decision? How much should you buy? How much should you sell? When should you buy? When should you sell? Well, it's all driven by data coming in here on the left-hand side. And of course, this whole pipeline is coming up with that buy and sell order decisions. And so starts with extracting features, then a process that gets referred to as alpha modeling that is forecasting or predicting how, say, a stock price will go, deciding the allocation of the portfolio, and then actually deciding on the buy and sell orders. Let's look at each of these in turn, and we'll see that some of these are sequential decision-making processes. So alpha modeling. Alpha modeling is a process of given information about a financial instrument, predict at time t if the price is going to be higher or lower at some future time point. So we're given this time sequence, and what's it going to be? And one way to do this, very simple way to do this, is take the average over a past period of time, maybe not all time, but some recent history, compute the average, and expect that the average will be that average is what it will be in the future, and make a buy or sell decision based on this idea. The idea that the stock will revert to the mean and the whether, and this is how it played out, and that's referred to as a mean reversion model. No deep learning here. This is just a very simple model for prediction. Now let's call that a zeroth order model. Another possibility is here's another sequence, and we're interested, in the future, maybe 2 different time horizons, what the price is going to be. And what we can do is we can fit a curve to that or a line and predict forward using that linear extrapolation what the price is going to be. And how well did we do? In the mean reversion model for that situation, we underestimated. Here, there's a slight overestimate of where we think things are going to go. And that second one is referred to as a momentum model. That's an example of a non-learning based alpha model. All right. So I started in the middle because that's clearly got a sequence in it and might be an opportunity to apply a sequence processing task. To mention feature extraction, what goes into the alpha model. The examples I gave use price, the previous stock prices. And those are generally referred to the price, and what you can measure about the market itself are referred to as technical features. This could be price, it could be the volume, how much is being traded. There's actually a spread when you go to buy something, it's going to be higher than when you want to sell it. So that's referred to as the bid-ask spread. These are features you measure directly from the market. Doesn't matter what instrument it is, doesn't matter whether it's Apple or Google or another company of interest. It's about, well, it's you look at the prices. Now you could actually look at the business itself and see how it's doing. Look at its annual report, look at the sales, use information, publicly available information to understand how the business is doing and make decisions based on that. It could be directly reported by the company or maybe inferred. You know, we start hearing about blockages at ports right now. And so maybe it's not a good time to be a toy manufacturer. So that would be more fundamental information. And then there's information that might affect the stock price about what's going on in the media. How are people feeling about it? What is the sentiment towards that particular stock? And you could be looking at the news, you could look at social media, you could look at analyst comments. All of these are indicators, each has a sentiment associated with it. Those can be combined together to make a forecast about how the stock price is going to move. And most of that information comes in very unstructured data, comes in Bloomberg television. It could be coming in off of your favorite social network of choice, and coming in as plain text and to be interpreted towards sentiment. And then there's non-traditional sources of information. If there's a lot of cars in a parking lot at Christmas time, maybe that retailer is doing really well. If there's container ships backed up in a harbor, maybe something that's based on exports is not going to do so well, and so on. So there's a source of information that might feed into an alpha model. Next up is portfolio optimization. So the alpha model has made a prediction about what we think each of the stocks will do. This is a listing, hypothetical, from six of 30 equities in the Dow Jones Industrial Average. And imagine this is one day and it's looking like P&G is going to be doing really well, Salesforce not so good. So what should we do? Should we go all in with this forecast into Procter & Gamble and buy it? And the issues that we'd really want to consider quantitatively is, well, how much do we already hold of each of these stocks? Maybe we already got a ton of P&G and really shouldn't buy more of it. Are we actually confident in these forecasts? Do we know that, are we feeling that we've got the data to know how Chevron is doing? How volatile have the prices been? Are they been pretty stable? Are they going up and down a lot? How diversified should we be? Should we really put all our eggs in one basket, or should we spread it out? If we're spreading it out, what does it mean to be spread out? How do we make that decision about how spread out to be? And then finally, we already own something and buying it isn't free. It's not a complete exchange. There's a cost associated with making a trade. How do we handle that? Well, all of these issues can be expressed together as a large-scale optimization problem. Their optimization is over all the possible ways you could spend your money or invest your money. And it's generally handled through optimization. The final piece of this pipeline is execution. And this is where we go to the market and actually buy and sell the stocks to achieve the portfolio that the portfolio optimization has suggested that we do. Now, it's important to note, when the optimization happened, there was some price determined, but share prices are not fixed. It's not like they're advertised at a store and you're guaranteed to go into the store and get it for the price that you wanted it for. Instead, it's governed by a market, and market forces market participants. So we're not passive observers. When we go out to buy something, the price might change. It might go up. Come in wearing a fancy suit and a nice watch, then you might get charged a bit more. So it's a market, and the more you try to buy, the price might move based on that. So decisions that has to be made in execution is, if we want to buy a lot or sell a lot, should we break it up into smaller orders and place them at different places? So in fact, there are not just one place where you can buy or sell a stock just because it's listed on New York Stock Exchange. There are other exchanges that sell and buy the same equities. When should the orders be placed? If you place them all at once, it's almost the same thing as placing one very large order. Maybe they should be spread out uniformly over time. Maybe we should be more systematic about it and responsive. What type of order should be placed? There are more complex orders than just saying buy it now or sell it now. There are things like limit orders and stop orders and so on. Finally, we'd like to have a model of what the impact of our actions is going to be to help us with our optimization and making decisions about buying and selling. And this is referred to as a market impact model. Okay, so this is the pipeline, and this is the way quantitative finance tends to break up the process of making buying and selling decisions. So not all of these, but these three blocks all have aspects of sequential decision making in them. Feature extraction, again, might be just at the level of text, looking and trying to estimate or determine sentiment. Alpha modeling takes in a history of past features, could be sentiment, could be technical features, could be fundamental features, and produces a forecast about how we'd expect a particular instrument to go. And then execution is dealing with the sequences of the actual buy and sell decisions that have to be made over time. So all of these have sequential aspects to it, which means I want to turn my attention now to how deep learning can be used to solve some of these problems. I'm going to sketch out deep learning, what it is for those of you who don't have experience in it, and then see how to connect it up into at least the alpha modeling process. Again, I'll remind you, if you have questions, please go to slido.com, enter the event name 2 Sigma Presents, and you'll be able to ask questions. You'll be able to pose questions there, and then later on a panel will answer those questions. Okay, so let's move on to deep learning. And deep learning is basically a type of neural network that's large. Neural networks are not new. They go back even before I was born. Frank Rosenblatt implemented sort of the first neural network in analog perceptron in 1958. So it goes back quite a ways. But the real heyday of deep learning has really happened started in the last decade. And what changed since 1958, besides computers getting a lot smaller? All right, so there are new network architectures. We'll see a version of Rosenblatt's perceptron in the next slide, but the new architectures really build off of that. The other thing, of course, is massive amounts of training data. When he was training a perceptron, it was a very, very small amounts of data. Algorithms have changed to accommodate the new architectures to train more deeper and more complex networks in reasonably effective but highly computational methods or requirements. And finally, we now have massive parallel computation, which is really needed to be able to effectively train this in our lifetimes, rather than using computers of old and even computers of not so long ago. All right, so Frank Rosenblatt's perceptron and the basis for most neural networks remains pretty similar and is illustrated here. So this is a single perceptron, and it's a node in a multi-layered network. It basically takes in a set of inputs numbers, x1 through xd, computes a weighted sum of those numbers, and then passes it through a nonlinear function that's referred to as an activation function here, g. So that could be expressed as a summation in an equation down below. It can be thought of as a dot product of the weights with the inputs. And there's another term that's referred to as the bias term. That's an offset, W0, that is an input. And we'll generally not show that bias term in any of the subsequent slides, just to make the slides a little simpler. Now, when Rosenblatt created the perceptron, his activation function was simply a threshold. Is the weighted sum greater than or less than a threshold? Now, that soon went away and was replaced by a softer version of a threshold, the tanh or sigmoid function. And the equations are shown here on the left. And if you stand back from a little bit of a distance, those functions look like thresholds. When they're less than a certain value, the value, say, of the sigmoid is 0. And when they're greater than a certain value, it's very close to a 1. But these are differentiable functions, which helps in our learning methods. The activation function has, to a fair extent, been replaced in the last decade with an alternative one called the rectified linear unit, or ReLU, or some sort of relatives or cousins of it. What does the ReLU do? Basically, it says if the value of, going back to the previous slide, the value of the summation part is less than a threshold, then it just outputs 0. And if it's greater than a threshold, it outputs the value. And that's a standard activation function that's being used. And yeah, there are modifications of this where it's soft at the corner and that it has a slight slope for negative values called a leaky reloop that's in there. All right, so that's a single layer of the network. Now these get combined, and that was what Rosenblatt introduced, but it was realized there were very quickly that there were limitations to a single node. And so a multi-layer perceptron or two-layer network shown here was introduced. Two-layer network has each of the circles is one of those perceptrons with its own activation function and own set of weights. And that can be represented as a pair of weight matrices, W1 and W2, associated with the first layer and another one associated with the second layer, and then two activation functions. All right, and that allows us to build out to a larger network. Now let's build an alpha modeling network from this, one that will predict the price of the stock tomorrow based on past measurements of it. And recall our alpha modeling when we talk about mean reversion and momentum. We'll now use a neural network. So we're given a sequence of daily stock prices, P1 through PT for the last T days, and our job is to predict the T+1 price. So we have our network that takes D inputs, and we want to produce a prediction. So to feed that in, we can directly feed the prices into a multi-layer network like shown here. We're going to have to eliminate the old history because we only have D inputs, and if T is bigger than D, we're not going to be able to handle all of the inputs. So we'll truncate everything up to time T. And we really only care about one output producing just the next price. So we'll call that, we'll have a single output instead. All right, now the network needs to be trained. What do we mean by training a network? Well, we need to be able to evaluate that functions that we'd seen before. We need to know the weights W. So how do we estimate W? Well, this is where training comes in. We need some examples. We need to look at, say, the previous history of how a particular stock had evolved over time. Let's look over the last 10 years and see how the next day related to the previous D days and set that up as a set of training data. So we have a pair of training features, X, and the price from tomorrow, PT+1. So to do training, we'll feed the features in, that sequence of previous information into an untrained or partially trained network, and we'll get out a prediction or forecast of the price. Shown here is PT+1 hat. Likewise, we have in our training data what the price was tomorrow given the training data. It's not tomorrow, it's, let's say, in 1918, in January, over the past month, what was the previous prices, and then what was tomorrow back then. And we'll compare our prediction P hat to the actual price through a function that is referred to as a loss function. It's a comparison function. It's one that's small if our prediction is perfect, it's 0 if it's perfect, and it goes up when they're different. And there's different functions that you could use for a loss. This is, part of the art and experience of training networks. But for this kind of problem, a typical loss is going to be simply take the difference between P hat and P and take its absolute value, or take that absolute value and square it. And that might be the loss function that we would use. So then that's for one pair of history plus future. Our training data is going to have many examples of that. As shown here, we have M examples. So we'll add up M examples from M examples, the loss function, and that's referred to as the total loss. So now our training is now turned into an optimization problem that says minimize the total loss relative to W, choose a value of W that minimizes the total loss over our training data. And that's easily said, perhaps a bit harder to actually implement. And there's a collection of training techniques for doing this. Rosenblatt simply used a form of gradient descent on his one perceptron to do it. Sometimes the method used in between is referred to as back propagation as a technique. And there are specific there's a collection of methods that has opened up that works effectively for networks as they get larger and larger. And the introduction of stochastic gradient descent in particular was a bit of a watershed in allowing large networks to be effectively trained. And there's a lot of other things that come into play that if you get into deep learning, you'll know what those things mean. So if you're really building an alpha model, of course, you're not just looking at one signal, just the past history. You're taking all those features that we mentioned earlier and combining them together, or at least a relevant subset of them that's going to be more powerful than just a single number as an input. And now we have, instead of just one number each time, we have the price, the volume, the spread. Maybe we have fundamental information that's maybe coming in slower. It's not happening day by day. We're not getting a new quarterly report every day. Sentiment might be coming continuously. Certainly the news groups are pretty active, chattering away, and so on. So we will have a variety of features that we can concatenate together at each time instant and use that for prediction. All right. The problem with this approach, however, is that using a fully connected network like this is that the number of weights that we're going to have to train can start becoming very large. In particular, if we're looking back in time, d steps, and we have many features n, even in that first layer of the network, we're going to have d times n weights in it. And that number of weights can become large relative to our amount of training data. So that becomes a problem. We're not necessarily going to be able to train a network to fully take advantage of what's available here. So this is where another class of sequence processing networks comes into play, called recurrent neural networks. So let me introduce recurrent neural networks by starting with the two-layer network that we'd seen previously. I've kind of drawn these things as blocks. The first layer has a weight matrix WXH and an activation function G. And then our next layer has a weight matrix WHY and another activation G2. So that's a two-layer network. To turn this into a recurrent network, we're going to make the input to this just one time step. And we're going to step through sequencing inputs. Let's say over the last 30 days, we'll have 30 inputs come in sequentially into the network. But we introduce this memory that takes the hidden layer after the hidden state after the first layer and feeds it back as part of the input, as to the input. And now the network is building state with each time instant. And that's referred to as a recurrent network, one that has a sense of memory to it, built into it, and feeds that backwards. So how do we train a recurrent network like that? Well, we can again use the techniques that we had used for a feed-forward network, like our multi-layer perceptron. We can use back propagation, but we have to do a trick to it. The reason we can't just use it directly, let's go back to this picture, is because we have the loop in there. The network we can no longer feed back information through that loop caused by the memory being present. So the trick is to unroll the network to say, well, it's not really going to be responsive all the way back to the beginning of time. It's only going to be back to the start of the sequence, say 30 steps ago, or d steps ago is drawn here. So we unroll the network in this fashion so that it goes back, and there are d of these units going backward in time. And this alone begins to look just like a feed-forward network. X1 goes through many layers, X2 comes in at the second layer, X3 comes in at the third layer, XD comes in at the second to last layer before it gets up to the loss. And by doing this unrolling, we turn what had a recurrence relation into one that is amenable to gradient descent techniques. Now, the trick here, though, that makes this thing tractable and not have the number of weights blow up is that the weights are shared between each of these elements. So WHH is in all of the layers. So we unroll the network, so it looks like a feed-forward network, and all of the weights are shared. Now, this is a deep network. The network we saw before in our earlier drawings were two layers. When we've done the unrolling, this network now has D layers going backwards from that X1 to XD over the time steps, plus the extra one near the top. So D+1 layers in this network. So it's deep. If it's 30 days, there's 31 layers deep into this network. Again, the weights are shared. Training these kind of networks can be difficult. And so there's been a number of issues identified during the training process. The process of stochastic gradient descent means computing gradients, and those gradients sometimes become very large. And that's easy to handle. There's methods called gradient clipping that can be used to handle that. Another issue is that the gradients may actually drop down to 0. And if you're doing a gradient descent optimization along the way, if they drop down to 0, you're not going to be able to make steps. So regularization is often a technique that helps alleviate this problem. But still, the information often doesn't propagate very far backwards down through all of those layers. And so the memory doesn't, even though the network might look at an early point in time, the networks don't seem to be very responsive to that. And so another class of networks got introduced called gated networks. And these gated networks, recurrent networks, called GRU and LSTM, have an advantage that they actually allow the information to propagate further back in time. So what's in a gated network? Well, rather than just the weighting, the weighted sum and the activation function, a gating network introduces a gate. This gate is not a digital gate, it's an analog gate. And the analog gate basically is like a spigot or a valve where the value of the gate determines how much of the information flows through. So you can think of it as just a linear function where two forms of analog gates are shown here. In the one on the left, the input A is modulated or scaled by capital gamma to give us an output C. That's one form of a gated unit. Another one mixes two signals, mixes A and B together, and gamma's a number between 0 and 1. And so it's going to take a proportion of A and a proportion of B. And A and B don't need to be scalars. They could be vectors. They could be a vector of numbers. And the input gamma is the length of those vectors A and B. So this is another building block. It's a differentiable building block. So it can be used in the similar optimization techniques that are used in multi-layer networks. So how do we build one of these networks? Well, the recurrent network I mentioned before is called an Elman network, named after Jeff Elman, who had been a professor at UCSD. There's another variation called the Jordan network, and Jordan was Elman's postdoc, now a professor at Berkeley. Anyway, the Jordan network takes the feedback or memory not from the hidden layer, but from the top layer, which itself has advantages that I won't get into here. If we redraw that Jordan network and that two-layer network in this fashion, so the second layer is pointing out to the right. And if we think about this back propagation through time, SI is the output, the state output of this unit, and SI minus 1 is the state output from the previous time step. And you imagine these things stacked up or arranged horizontally over time if we're doing training. All right, so this is just that same two-layer network redrawn. Instead, we'll replace that top layer with a gated unit. There's no weights inside of that. Where the weights will come into play is controlling the gating signal, how much of the input is allowed through. And that's got a simple one-layer weight matrix combined with an activation function, usually a sigmoid, was shown earlier. And that gating function combines the previous state, SI minus 1, with a computed new state, SI tilde, shown here. And that gate that's shown in this, the gate is referred to as an update gate. It's going to update the previous state with a potential new state, and how much it's going to combine the two together is determined by the gating weight. That's combined with another gate, another analog gate in here, which has a function of resetting the state, bring the state back to say 0, at least for some of the values in there. And this network, all of the components of this are differentiable and therefore trainable by techniques like back propagation that we had mentioned earlier. This kind of network, the GRU, and this is simplified, is one that has a longer memory. It's one of two main recurrent gated networks. There's the GRU, and the older one actually is the LSTM, which stands for long short-term memory, the longer short-term memory. So it's not remembering years ago, but it's remembering maybe 30 steps ago fairly well. Anyway, the LSTM has more gates and more parameters and has been around longer. The GRU is a newer gated recurrent network with fewer parameters and is often said to work better when the amount of training data is small. That should be data, not dates. All right. So these are networks that commonly get used for deep learning for sequences. Now, more recently, there's been more recently, meaning in the last 5-6 years, other architectures that have also, kind of taken hold and surpassed even the recurrent networks for a variety of reasons. The recurrent networks still remain difficult to train. They don't necessarily focus attention on the right parts of the history in there. And so words that you may have heard in the deep learning literature, convolutional neural networks, which have really had profound impact on my field in computer vision and image analysis, can also be applied to sequence data. There are 1D convolutional networks instead of 2D would be used for images because it's a one-dimensional over time sequence. If you want to get a very large past history in here, those convolutional networks don't train so well. So dilated networks are an extension of that allow one to go back further in time. Attention methods to focus on particular parts of the sequence, originally used within the context of RNNs, became important. And then what is attention? Attention, it turns out, we said gates are an analog, the gates that are used in neural networks, analog versions of a digital gate. The attention mechanism is essentially a form, and the language of it is the form of a key value store, or a dict as we'd think about in Python, where you have a dictionary with a key and a value, and you have a query. Now, in our programming languages, you have a query that will match the key and then output the value. This is a soft differentiable version of a key value store. And that's the kind of core part of what's used in attention. And then transformers were introduced as a method that said, well, we don't need to take attention and put it in a recurrent setting. Let's just focus in on this attention mechanism itself. And that's had a very large impact, especially in, well, as I say, in natural language processing, a big one. There's an architecture called BERT that builds off of it. But even now in my own field of computer vision, visual transformers are now largely exceeding the accuracy that convolutional neural networks had been given. All right, going even further than the kind of methods that we had talked about is reinforcement learning. So reinforcement learning comes about when we talk about trading and interacting with the market. When we participate in a market, our actions affect the market. The price of something will change because of our own actions. And the methods we've talked about now have been more supervised, where we have a set of training data that doesn't really take into account our own actions within that market. And then reinforcement learning is something that does that. Reinforcement learning is an end-to-end method and optimizes sequential decision-making, buying, selling, buy, sell, and so on, which ones we're in, to maximize not a single reward, but rather the cumulative reward over time. And RL has been extremely successful in games, and it's been demonstrated in some robotics. So DeepMind, demonstrated through AlphaGo, playing superhuman playing. OpenAI and with Dota 2 showed in real-time game playing. We can also use RL to do extremely well. Applying RL in finance requires some things. It's an expensive process. It's been very successful in games because the games are very, very well defined. In our world, what do you need? Well, you need a good simulator that simulates what the effect of your actions is going to be. You need good software for implementing RL. And we leverage things like OpenAI Gym and Ray RLlib and other sources, as well as things that we develop ourselves to do reinforcement learning. And you need a lot of computation. There's a lot of simulation that's needed, a lot of examples that need to be run. So you need not only just the hardware, but you need a software infrastructure that will support the scale that's needed. All right. So let me just kind of wrap up now so we have some time for questions. So first thing to say is, look, many parts of the investment pipeline require inference over sequences. I showed the pipeline and argued that at least 3 of those steps out of the 4 are problems of sequential decision making. Deep neural networks can and are being trained to implement these parts of the pipeline in various forms. Of course, I haven't given you the details. There are a large number of people working in a place like 2 Sigma that are needed for doing that. And so for this kind of work to occur at a place like 2 Sigma and operate the scale that we need, well, you need lots of data, and 2 Sigma has more than 10,000 data sources of information and takes in more than 20 petabytes of new data each year. So the price data is relatively compact. All of that other information that's in all those other forms, that gets to kind of become large. You need lots of computation. You need CPUs, GPUs, TPUs. You need a good solid software infrastructure, distributed systems, and particular software packages tailored to our learning methods. And of course, we need lots and lots of creative people to bring this stuff to reality. 2 Sigma scale, we've got $58 billion of assets under management. We trade in 8,000 equities. It's a lot. And we trade, 300 million shares per day. So there's a lot of decisions that have to be made. They have to be made fast. And of course, they're not made by people. Emotions don't cloud the decision making. They're done through these methods. So with this, I'd like to turn our attention over now to taking your questions. Again, I'll remind you that you can submit questions on slido.com. Use the event name 2 Sigma Presents, and there you can upvote and downvote as well on those questions if you haven't already. I'm going to be joined by a collection of panelists. Niranjan is part of the AI core team where I'm working at 2 Sigma. He'll moderate it. And then I'm joined by 2 members of the recruiting committee, Kyle and Thunder, who will also answer questions. So with that, I will turn it over. We'll have the panelists join the conversation.
All right, looks like we have quite a few questions on Slido. So let me start with the first one here. Would it be possible to have a copy of these slides after the talk? Maybe Carl?
Yeah, sure. So we will actually be releasing a video here in the next few weeks, both to our website as well as LinkedIn. So definitely look out there. However, we will unfortunately not release the slides themselves. But again, video will be out there, so you'll have all the content.
Okay, thanks. Next question. How does the lack of explainability, interpretability associated with deep nets affect strategy development at stages along the pipeline, if at all?
That's a great question. Some use cases are indeed black boxes where you can explain it based on its past history, but you don't know what is being done by decision making. And there are architectures that might introduce intermediate layers of representation that are interpretable, and that would allow some degree of explainability.
Our next question is, how much do you regularize for black swan events such as COVID-19, which totally perturb previous distributions? Do you use all else fails heuristics to stop trading at that point?
So, different, I didn't really get into time horizons in the discussion, but there's some trading that happens, quickly, that's going to make decisions on seconds, sub-seconds, minutes through the day. And the distribution of decision making, the way people respond during an event like COVID may be different than what happens beforehand. And then there's other short-term market events that can happen. The Fed makes an announcement that's going to cause perhaps some sudden change in it.
Right. I think we also have human traders who monitor these systems in events of market duress. So we do have a stop button, I guess, for extreme market events during it. Next question. How do these deep learning approaches interact with the hypothesis of an efficient market?
So if the, I mean, so the market is efficient, to a degree, right? So there's a time before the market responds to information. And while everybody has access to the same information, you hope in what we try to do that we can either respond a little more quickly, responsively, assimilate the information in a slightly different way than others have done it, and combine larger amounts of information than the entire market can operate on, and therefore have a chance to that the market is not actually fully efficient, that there are inefficiencies where there is an opportunity, and by participating in itself, the market itself does become more efficient.
Are there aspects of computer vision relevant to sequential modeling in finance? Also, are you looking for interns? So I guess you can answer the first question, David, and Tyler can answer the second one.
Yeah, if you were to look at the early stage of the pipeline where you're trying to extract features from unstructured information, that part of the pipeline, there are places where there is image data that can come in and can be used. And there are companies out there that are vendors of information that actually do that kind of processing. I don't know, probably not supposed to name them by name, but there are companies that take satellite information, for example, and provide analyses of what's going on in harbors, or what's going on with the amount of oil available in tanks, or how many trucks have left a port of entry, to be able to provide that kind of information. So there's a place in the early stages for direct image analysis. Otherwise, for myself, there's a lot of the methods and thinking that goes into computer vision that turns over. So we've done work on video classification, some of my PhD students, and some of those ideas apply here in sequential decision making.
And Kyle or Thunder, would you like to take the second part?
Yes, so on the internship recruiting side, we are very actively recruiting for engineering, for modeling, so that's quant research, at Two Sigma Investments, as well as Two Sigma Securities. So if you're interested, please, go online to Two Sigma internships. You can look for us. There are applications available. We will continue to recruit, into spring, but the earlier that you apply, the sooner we can engage with you and make sure that you find the right home.
Thank you, Thunder. Next question is, it seems like there is a difference between an AI researcher and a quant researcher at Two Sigma. Are QRs using deep learning, or is it only the people in the AI research team?
So I can touch on that. So there are pockets of usage of deep learning throughout the organization. So the different roles that we have out there do map to different teams. However, we do hire, kind of take a little bit more of a pipeline approach to hiring. So whenever we evaluate anyone that applies into one or all of those roles, it's kind of, we evaluate in an inclusive fashion. So and we ultimately, throughout the kind of initial stages and conversations that recruiters have with potential applicants and candidates, as well as through the interview process, discern which areas within Two Sigma are the appropriate areas. But yes, there is definite deep learning application throughout, again, a number of areas.
Thanks, Kyle. I guess another question about available roles. Are there any roles working on sequential modeling teams for recent college grads, MSc level?
I can take that one as well. So there are, and kind of similar to what I had mentioned, feel free to apply in, twosigma.com/careers. I know we'll be sending that out also via email. So you'll have a direct link there. Take a look. There are a number, there's probably a couple hundred roles that are actually posted. Don't get overwhelmed. Again, if you see a few, you can search, via keyword, kind of read through, see what looks interesting, apply in. A recruiter, again, if there may be interest there, we'll get in touch with you, and we'll talk to you a little bit more about the application. If it's sequential modeling, again, we'll talk with you through that and map you to the correct interview process.
Next question. So how do you address the lack of stationarity in financial time series? Deep learning works well when the distribution of the features does not change from in-sample to out-sample data.
Now that's a fantastic question, and really is a crux problem that we confront in many ways every day. And it certainly, deep learning works best when the future looks a lot like the past. And so, parts of things are simulatable, parts of it are not. The extent to which you can simulate and predict and introduce domain transfer methods, that using that is where you have a chance to address those problems.
Next question. How do you quantify the predictive uncertainty of an output that is estimated with a deep neural network model? In other words, how do you know if you can trust a model?
Well, I guess this is true for almost every model that you have, or anybody who claims to have any prediction or forecasting ability. The proof is in the past ability for it to run. And at some point you have to deploy and measure and test and evaluate.
Right. And I guess also, since the model gets to buy and sell so many times, I guess it doesn't have to be right every time. It just has to be right more often than not.
That's actually a great point that I should have brought up. In the work doing deep learning in this environment is very different than many other ones. So when we try to do things like language translation or speech recognition, the target is 100%. We want to be 100%, right? In this world, if you're better than 50%, right, you have an edge, and you can try to do take advantage of that better than 50%. So it is a very different kind of world. It's one where the error rates are extremely high compared to many other problems that I've looked at in the past, which has made it extremely interesting.
What are the current research areas of deep learning and neural networks that have promising implications for quantitative finance? Some of the latest research.
Boy, there's almost none that isn't really of interest. So that's almost a very, very loaded question. Reinforcement learning, is an area that's certainly of interest. Anything that allows domain transfer or is robust to domain shifts would be very, very valuable. Architectures that can work, that are trainable more quickly, that are sparser, are all kind of interest. So there's almost no part of going to ICML or ICLR that isn't really of interest to some degree.
I don't know if you already addressed this, Thunder, but doesn't hurt to answer again, I guess. When do you start recruiting QR interns?
We have started. We want you to apply, and we will recruit into spring as well. And I think I saw another one just about the undergrads, and so we're recruiting across all degrees, so bachelor's, master's, and PhDs.
Thanks. I guess in data storage question, are there data storage problems in this process? How are they addressed? Are any data compression techniques helpful in this?
Yes, yes, and yes. this talk has focused on, if you will, one slice through what we do at Two Sigma. I mean, this is an example of deep learning applied to the modeling process. However, there is an enormous number of storage challenges. As mentioned, with 20 petabytes a year of new storage comes in, it needs to be accessible to the computation that's available. It is, some of it's in the cloud, some of it is on premises, some of the computation is happening in different places. The real-time part for the trading system has certain requirements, which might be different than the requirements that are for a researcher that's developing a new model. So the engineering team is diverse in what it's working on, from storage, the physical systems, the layers that sit on top of the physical systems, and Kyle could probably speak to the whole organization to an even better degree than I can.
How do deep learning models fare in practice compared to statistical modeling like basic regression, kernel density estimation? And how do we balance bias variance trade-off, data scarcity versus model capacity?
Oh, they both have roles to play. If the deep model turns into a degenerate form of a linear regression, it's not interesting as a model. If it provides something that is like an orthogonal source of information, then it's an accepted piece of it. And certainly the history is of using linear models, and so nonlinear models like recurrent, like these networks, provide new opportunity, perhaps on the same data, to get more value.
Cool.
Okay, looks like.
Yes, thank you so much. We're actually over time, and
Oh.
I don't want to keep everyone too late. So thank you so much for joining us today. A huge thank you to Professor David Kriegman and to our other panelists, Ranjan, Kyle, Thander. Thank you. To learn more about Two Sigma, check out our blog at twosigma.com/insights. You can check out openings at twosigma.com/careers. And if you have any questions regarding applications, please contact recruiting@twosigma.com. Thank you all so very much for being here today.